All right, day 17 notes. We're going to look at SOHCAHTOA today, but we're going to do it in terms of trig stuff. But just want to review you a little bit about SOHCAHTOA. You should have seen this before now, but the important thing about SOHCAHTOA is it's all based on where this theta angle is. And so based on this triangle that I have, and notice that it is a right triangle, we can only use SOHCAHTOA with right triangles. But based on this, where theta is, this is called the opposite side because it is opposite of my angle there. This is called the adjacent side because it is next to my angle. And then always opposite the right angle is called the hypotenuse. So using our little acronym here, SOHCAHTOA, the sine of theta, the sine of this angle, would be equal to the opposite side divided by the hypotenuse. In other words, the sine of this angle is equal to that ratio, and that's the SOH. And then cosine, adjacent over hypotenuse, and then tangent is opposite over adjacent. So we're going to use that in the lesson that we're doing today, that I'm going to show you. So I'm going to show you a couple examples here, and this will be for class tomorrow. We're basically going to find all of our trig functions using this information. All right, so let's look at example 1 here. I'll zoom out a little bit for you. It says find the exact values of all 6 trig functions given an angle in standard position and a point on its terminal side. So what this is saying is you have an angle that's in standard position. We don't know the measure of that angle, so it's just going to be theta, just any angle. But we do know that its terminal side goes to this point, -4, 1. Okay, so this is the answers that we're looking for. We want to find the cosine, sine, and tangent, and the secant, cosecant, and cotangent. Now here's the nice thing. Once we know the cosine, sine, and tangent, which we will get from SOHCAHTOA, all we have to do is take the reciprocal or flip the fractions, and we will have the secant, cosecant, and cotangent. So let me show you how to work this problem. Now for all the problems that I do on these, I always draw the same triangle every time. So what I'm going to do is I'm going to draw a triangle here, a right triangle, and pretty much I'm drawing the same triangle that I drew in the above diagram. And I'm going to put theta down here. Okay, alright, and when I draw this triangle, what I'm going to do is I'm going to look at it in terms of the XY axis, okay, or the XY plane. So this side right here is the horizontal side. And if we're looking at the horizontal side on the XY axis, that would be the X part. Horizontal is always X. When we count for X, when we're doing points, we always go left to right for that. So this would be the X portion. The vertical side, the vertical leg, will be my Y portion because Y is my vertical axis. So what I'm going to do is I'm actually going to take these points right here. -4 is an X coordinate, 1 is a Y coordinate, and I'm going to label my triangle -4 on the horizontal or the X part, and I'm going to put the 1 on the vertical or the Y part. Now I know that a distance cannot technically be negative, but remember we're talking about the XY axis, the XY plane here. So really this triangle, although I've drawn it this way, it technically is over in quadrant 2, which means it has a negative X value and a positive Y value. Okay? Now, in order to find the hypotenuse, we can do Pythagorean theorem here. And the nice thing is, once we find the hypotenuse, we can use SOHCAHTOA to get cosine, sine, and tangent. So the first thing I'm going to do here is the Pythagorean theorem, a squared plus b squared equals c squared. And so it doesn't matter what you use for a and b. C is always the hypotenuse, so I'm just going to go 1 squared plus -4 squared equals c squared. So that's 1 plus 16. We add those to get 17 equals c squared, and then we square root both sides, and we get the square root of 17 is c. Alright, so that is my hypotenuse, radical 17. Now, if I know all 3 sides of a right triangle, then I can use my SOHCAHTOA ratios. So what I'm going to do is I'm going to use those. So to find the cosine, that is the adjacent over the hypotenuse. Now, when I do adjacent over hypotenuse, in this case, if we're doing cosine, and I do the adjacent over the hypotenuse, we get a radical in the bottom, which means I have to multiply by the square root of 17 to simplify it, and we get negative 4 radical 17 over 17. That is my answer for the cosine. Okay? Adjacent over hypotenuse. Now for the sine, I'm going to do the same thing, except I'm going to do opposite. Here's my opposite side. Opposite over hypotenuse. And here again, the radical's in the bottom, so that's not simplified. So when we multiply by radical 17, we end up with the square root of 17 over 17. And there is my sine. And then to do the tangent, we do opposite over adjacent. So in this case, I don't have any radicals to deal with. My opposite is 1, my adjacent is negative 4, so that is just negative 1/4. Or if you wrote 1 over negative 4, that's fine as well. Okay? Now, to get the secant, cosecant, and cotangent, all I have to do is the reciprocal of these. Now, what I would do is I would go back to the original problem. When I did the cosine, and I did adjacent over hypotenuse, I had negative 4 over the square root of 17. I'm actually going to flip that one. Because when I flip that one, what I end up with is negative square root of 17 over 4, and I don't have to do any simplifying. If I were to flip this one right here, when I flip it, I would end up with this, and now I still have the same problem with a radical in the denominator, and I would have to go through and simplify that. So it's easier just to go back to the original where you did adjacent over hypotenuse. Same thing for sine. I originally did 1 over square root of 17. So when I flip that, I get the square root of 17 over 1. And that's my cosecant. And then when we flip the cotangent, we get negative 4 over 1, or just negative 4. Alright? So that's if you're given a point on the terminal side. This is what you'll do every time. Your x will always be here. Your y will always be on the vertical. Alright, we'll do another example in class tomorrow where I'll give you a little bit more information, maybe tell you what quadrant it's in, and give you one of the trig functions, but we're basically going to work the problem the same way. But this right here is the first example for a point on the terminal side. So we'll see you guys in class tomorrow.